Now that we've learned about solution concentrations, we can apply that to stoichiometry. Molarity relates moles of solute to liters of solution. And in stoichiometry, we need to know about the moles of the compounds because that's how we know the ratio in which they react. A lot of reactions occur in aqueous solution, and so the easiest way to measure quantities is by the volume. If you know the molarity, you can find the moles. So this is the plan for, come on, pointer, there it is, for the path for stoichiometry with solutions. But really this is just a variation of what I told you earlier. Grams to moles to moles to grams. That's still, I recommend you start with that, grams to moles to grams. And what you're going to find here is that instead of a mass, they're going to give you a volume and a concentration. So you're going to start with a volume. And then they'll mix it up too. Sometimes they'll start with a volume and then they'll ask you for a mass. Or you'll start with a mass and they'll ask you for a volume at the end. Or it could go volume to volume. There's all these different ways that you can do it, and what I'm trying to teach you is an approach that you can easily apply to any of these situations, right? Sometimes they might be volume to moles, and you just stop there. Well, it's all a variation of grams to moles to grams. So start there and then see what happens. So here is a solution stoichiometry problem. What volume in milliliters of a 0.105 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? So the first thing is we read the whole question, and then we look for numbers. And there's several numbers here. There's this one, and this one, and this one. And what are we looking for? Volume in milliliters, right? So identifying the numbers, we're going to pull these out and write them down. With stoichiometry, I highly recommend using the equation to organize them. So here's a molarity of HNO3. So under HNO3, I'm going to write 0.150. What does capital M mean? Moles over liters. So we want to write moles over liters. Okay. 35.7 milliliters of, that's the sodium carbonate. And it gives us that concentration. Also moles per liter. And then what we're trying to find is the volume of the nitric acid. So the question mark, how many milliliters? So this is not a dilution equation, right? There's no mention of diluting. And we've got two different compounds involved. This is stoichiometry. Do not use M1V1 equals M2V2. Do not. So stoichiometry. We think grams to moles to grams. And then see if we need to modify that. Well, we're trying to find at the end, we're trying to find volume in milliliters. So we got milliliters here. And in the beginning, we've got, this is our starting point, the sodium carbonate. We have a volume and a concentration. Moles per liter, that's going to be a conversion factor. So we're starting here with milliliters. So this is very common to have your volumes given in milliliters because in, chemistry education, we do things in small quantities, right? So we don't measure our experiments in liters. We'll use 17 liters. That's a lot, right? You probably use 17 milliliters. So we'll see milliliters all the time, but then the molarity is moles per liter. So we have to deal with this unit conversion thing. And there's a couple of different ways that you can deal with it. But I'm going to show you something called millimoles. So let's just look at, let's think about a fraction, maybe 1 over 2. So if I multiply that by the same thing on the top and the bottom, I get 2 over 4. Does this represent the same quantity as that? Yeah, it does, right? We could also write that as 1 times 2 over 2 times 2. And we could, the 2's cancel out. It's the same thing. Everybody agree with that? So I'm going to show you what you can do with the molarity to have it be milliliters instead. So if we take that 0.108, and that's moles per liter. If I multiply by milli, 10 to the minus 3, on the top, we're going to get millimoles. And if I multiply by milli on the bottom, I'm going to get milliliters. This is the same as saying 0.108 times 10 to the minus 3 moles per 1 times 10 to the minus 3 liters. Everybody okay with that? So I can interpret moles per liter as millimoles per milliliter. Okay? And then I don't have to convert between liters and milliliters all the time. If you go on to take Chem 1B, really try to get a hold of this millimole concept because it's super useful there. Okay, so what can we do here? So really what we're doing is we're doing milliliters to millimoles to millimoles to milliliters. It's got milli all over the place, right? I meant to bring my millimole, and I forgot. Maybe I'll bring her back for the exam. So we're starting with our volume of sodium carbonate, 35.7 milliliters. And it's important to say what compound this is. I've got 3 arrows, 3 conversion factors, very typical for stoichiometry. After milliliters of sodium carbonate, we're going to get millimoles of sodium carbonate. And the next is what? Millimoles of HNO3. Oops, not millimeters, millimoles. And then finally at the end, milliliters of HNO3. So milliliters to millimoles to millimoles to milliliters. Any questions about that? Concerns? So I'm going to just follow my dimensional analysis strategy and take this unit and bring it down here. So that's milliliters of sodium carbonate. And those are going to cancel. Down here, I'm going to get millimoles of sodium carbonate. And those cancel. And down here, I'm going to get millimoles of HNO3. And those cancel. Millimoles and milliliters, the relationship is the concentration, the molarity of that solution. Let's just do this. Millimoles per milliliter, right? So 0.108 millimoles for every 1 milliliter. Where does this mole ratio part come from? The equation, right? So up until now, we've been talking about it in terms of moles. 1 mole of this for 2 moles of that. Well, you could also say 1 millimole of that for 2 millimoles of the other thing, right? So 1 millimole of sodium carbonate, 2 millimoles of nitric acid. And then here we've got volume and moles again, and that's this concentration. I wish it was so easy to move things in real life. So the 0.150 is on the bottom with millimoles, and 1 is on the top with milliliters. We didn't have to calculate any molar masses, right? If it was mass to mass, we'd probably have 2 molar masses we have to calculate. But here, they give us the concentrations, and so it actually goes much faster. So we've got 35.7 times 0.108 times 2 divided by 0.150, and this is going to give me 51.408 is what my calculator says. No, we don't actually. Because that's here in the milli. Mm-hmm.
But if it was liters, you have to.
Yes, if you converted this to liters and did moles to liters and moles to liters, you'd end up with liters of nitric acid, and then you'd have to convert to milliliters. Yeah. How many sig figs? 3. So 51.4 milliliters of nitric acid. So for this aqueous reaction, if we were using this volume and this concentration of sodium carbonate, what we just calculated is the volume of nitric acid that we should add so that we don't have a limiting and an excess reactant, so they're both going to react mostly completely. Any questions? This is a very, very common type of calculation in Chem 1A. Here's another one. This one is labeled conceptual, so we shouldn't have to do calculations. Consider this reaction 2A plus B makes C. What is the limiting reactant if you mix equal volumes of a 1 molar solution of A and a 1 molar solution of B? The limiting reactant. These can be hard to think about. I prefer questions that actually have numbers in them. And so you can do it that way, but you have to make up some numbers. So it says equal volumes. So I could pick whatever I want. What if I say it's a liter of each? That'd make things easy, right? Because if I have 1 liter of solution A, and that's 1 mole per liter, then I have 1 mole of A. And I have 1 liter times 1 mole per liter of B, so I have 1 mole of B. This reaction says I need 2 moles of A for every 1 mole of B. I need twice as much A. Do I have twice as much A? No. So what's the limiting reactant? It's A. And if you're still like, wait, what? Well, let's go ahead and do what we've done before. Calculate the amount of product that can be made, right? So from 1 mole of A, there's 1 mole of C for every 2 moles of A. So I'd get half a mole of C and 1 mole of C for every 1 mole of B. So I'd get 1 mole of B. Which one's smaller? This one's smaller. So this is my limiting reactant. Any questions? Sometimes questions like this are harder to answer because we're accustomed to dealing with all the numbers, and this is asking us to just step back and think about it. But that's good because it helps us to understand better.